Good evening, everyone. I am B. Anusha, pursuing BTech third year in the stream of Electronics and Communication Engineering. Today, I am going to give a presentation on the topic of temporal difference learning in machine learning. Introduction to the temporal difference learning. Temporal difference learning is also denoted as TD. Is a reinforcement learning and method that combines ideas from Moto, Corbo methods and dynamic programming. Here this shows the temporal different learning at each time setup. Historical context and development of temporal learning. Temporal difference learning was introduced by the Richard S. Sutton in the earliest 19th century as a way to improve a reinforcement learning algorithms. It bridged the gap between Monte-Carlo methods, the required complete episodes, and dynamic programming, which requires a complete model that helps the environment. The fundamental algorithms such as TDO were pivotal in advancing the field of artificial intelligence and adaptive control systems. Key concepts and definitions of temporal difference learning. The core idea of temporal difference learning is use of a temporal difference errors of updating the value. Estimates. The value difference function estimates how good a particular state or state action pair is based on the expected future rewards. Temporal difference methods operate incrementally, updating their estimates step by step when new data becomes valuable. Future states, incomplete sequences, bootstrapping temporal difference. Here the image shows the learning concepts of temporal difference learning step by step. The TD of zero algorithm. The TD zero of algorithm simplest form of TD learning difference between the successive predictions. The updated rule involves adjusting the current estimates towards the observed rewards plus discounted estimates to the next value. It is particularly substituted for the online learning in because it is particularly suited for the online learning in environments where the data arrives sequentially. The TD errors and its significance. The TD errors often denoted as impulse measure the disparity between the predicted and actual outcomes at each step. It is calculated as del of r plus v of s minus v of s, where r is the reward, alpha is the discount factor, v of s is the current value estimate. The v of s in the next state is estimates. The error signal drives the learning process, allowing the model to improve its predictions. Discount factor and its role. The discount factor gamma 0 less than gamma less than 1 determines the importance of a future rewards in the value estimation. A high gamma value long-term rewards promoting more fragmented decision making, while a low gamma emphasizes the immediate rewards. Proper tuning of gamma is crucial for the balancing of trade-off between short-term and the long-term outcomes. Policy evaluation with TD learning. TD learning is often used to evaluate a given policy by estimating its value function accurately. One of the value function converges its informed decision making or serve as a foundation for the policy improvement. The process is central to algorithm like TD0 and forms the basis of policy iteration. Actor critic architecture. Actor critic methods combines policy and value learning with the TD learning typically used for critic. The critic evaluates the current policy, providing feedback via TD network with the actor updates policy accordingly. The architecture enables the efficient learning in complex environments with a continuous or high dimensional space. Deep reinforcement learning in TD methods. Combining TD methods with a deep neural network leads to deep Q networks. DNQs enable learning in high dimensional state spaces. DNQs use experience, replay, and target networks to stabilize turning, leveraging the TD errors in a updated value estimates. These advantages have led to breakthroughs in playing complex games and robot control. Various in TD learning. Variants such as TD lambda introduce eligibility trace to combine n-step returns balancing bias and variance in estimation, convergence and stability. Under certain conditions such as fixed policies and appropriate learning rates, TD algorithms are guaranteed to learn true value function. The convergence proves reliefs on the stochastic approximation theory and properties of a Bellman equations. Practical issues like function approximation, exploration, and non-stationary environments require careful algorithm designs to maintain stability. Applications: TD learning is widely used in robotic game playing, personalized recommendations, and financial modeling. Its ability to learn decision-making systems. Challenges: TD learning can suffer from instability and divergence, especially when combined with the complex function algorithms. It may require subsequential exploration and careful balance between bias and variance to achieve robust performance. Future directions in TD. Research is ongoing to improve scalability, stability, sample efficiency of TD algorithms. Integrating TD methods with the learning continues to unlock new capabilities in artificial intelligence. Advantages in meta learning and multi agent RL are expanding the applications and robustness of a TD learning. Conclusion: in TD learning, it concludes that cornerstone of a modern reinforcement learning that effectively bridges the gap between MC methods and dynamic programming (DP) by leveraging bootstrapping and sampling. It provides a versatile framework for training intelligent agents in the complex real-world environments without requiring a perfect model of system dynamics. Thank you.